This is a separable differential equation that is pretty common. It comes up as a model in a lot of different situations, and we want to kind of investigate it. Just looking at this differential equation, the way you would solve it is you'd say, well, this 4 is a rather boring function of x, and then this y is a not too much more interesting function of y. So I'm going to divide both sides by y. And then I'm going to integrate both sides with respect to t. So I'll integrate my dy dt over y with respect to t, and I'll integrate my 4 with respect to t. Now dy dt times dt, that's just dy, so we have dy over y on the left hand side and 4 dt on the right hand side. Now, the antiderivative of this would be the natural log of the absolute value of y, and the antiderivative of 4 dt would be 4t. Both of these integrals come with their own constant. I'll just combine them over here on the right-hand side. Now, solving for y, I see that the absolute value of y is e to the 4t plus c. We could think about e to the 4t plus c as e to the 4t times e to the c. Now c was an arbitrary constant, so e to the c would be an arbitrary positive constant. So arbitrary positive constant here. So I'm just going to be sloppy and take that constant and rename it c. So we have the absolute value of y is this arbitrary positive constant c, which used to be e to the c, times e to the 4t. Okay, so this has to be positive, but this says the absolute value of y has to be that, so y would be plus or minus this arbitrary constant. I'll just absorb the plus or minus into the arbitrary constant. Now my constant can be positive or negative. The last step we want to do is just to figure out what should that constant be. We can see we have y as a function of t is equal to some constant times e to the 4t. So if we plug in 0, y of 0 would be c times e to the 4 times 0. That would be c times e to the 0. E to the 0 is 1. So y to the 0 is c. So the meaning of the constant is the value at y at time 0. And we were assuming that we would call the value of y at time 0, in this case y naught, the initial value of y. So we now have our solution. Y of t is this initial value of y times e to the 4t. Okay, now this was just one example where we had the specific constant 4, but we could go through this same derivation with any non-zero constant here instead of a specific constant. It would always turn out to be the same anyway, whether the constant was 4 or some other value. Of course, we would want it to be non-zero, because if it was 0, we'd have dy dt equals 0. If the derivative of a function is 0, that function must be constant, so that'd be pretty boring. But if r isn't 0, then it would take just a little bit more to solve this. We divide both sides by y, and then integrate both sides with respect to t. And of course, dy dt times dt is dy. And on this side, we have the antiderivative of r dt. Let's integrate both sides. We get the natural log of the absolute value of y. And over here, we get rt, put in our arbitrary constant c. This says that rt plus c is the exponent you put on e to get the absolute value of y. So we have the absolute value of y is e to the rt plus c. Of course, again, we could write that as e to the rt times e to the c. And I'll just be sloppy and say, well, we've got e to this arbitrary constant c. That's just some other arbitrary positive constant. I'll be sloppy and call that c. So we really have that the absolute value of y is some arbitrary positive constant times e to the rt. But then y would be either plus or minus some arbitrary constant, which is again just an arbitrary constant, so no sense in watching out for that plus or minus. And the meaning of c, of course, we have y of t as some constant times e to the rt. We can see if we plug in 0, we get out c times e to the 0, so just c, but then that's supposed to be y naught. So the meaning of c is the initial value of y. So we have yt equals y naught e to the rt. Okay, so anytime we see an equation that fits this form, Then we know what the solution is. But we're going to use that over and over again. The solution of dy dt equals ry, where the initial value of y is called y naught, is y of t equals y naught e to the rt. Good. Let's look at a situation where this comes up. Under ideal conditions, cells of a certain type of bacteria divide at regular intervals. You notice that if you start with 1 microgram, after 4 hours you'll have 13 micrograms of this particular bacteria. So if you begin with 13 micrograms of bacteria, how many will you have after another 3 hours? Well, if you think about the way bacteria divide, it should be that the increase in the number of bacteria, or the change in the number of bacteria, should be proportional to the number of bacteria. Since each bacteria has the same chance of dividing in the next time period, then that should be the correct model. The rate of change should be proportional to the number of bacteria. Okay, well, that model we know the solution to. We've done it, right? We know that if dy dt is some constant times y, then this is the solution. So we know that the number of bacteria as a function of time should be the initial number of bacteria times e to the rt. So the question is, if we want to know how many bacteria we have at some time, we're going to need to know what time it is, but also we'll need to know what's r and what's y naught. But they give us some information here. They say if we start off with 1 microgram, so y naught is 1 microgram, and we wait for 4 hours, then we'll have 13 micrograms. So if you start with 1 microgram, right, then you know y naught's 1, and you know that if you wait 4 hours, the formula that tells you how many bacteria you have in the future should be this, right? But that should turn out to be 13. We can use that to solve for r. The first thing I'll do is to take the natural log of both sides. So since 1 times e to the 4r is just e to the 4r, I'll just take the natural log of that. Okay, and this is the exponent you put on e to get e to the 4r, which is obviously 4r. So the natural log of 13 equals 4r. So now we know our constant r is the natural log of 13 over 4. So we have our model then is that the amount we have at any future time will be the amount we start with times e to the natural log of 13 over 4 times t. So now we can go and answer this question. If you begin with 13 micrograms of bacteria, that's saying that y naught is 13, and you're going to wait until t equals 3 hours. We want to know what's y, right? So we want to know what's y at time 3. Well, y at time 3 would be y naught, which is 13, e to the natural log of 13 over 4 times t, which is 3. So we can just crank this out to figure out what we've got. Let me pull up my calculator. And I'll just take, let's see, I need 13, so I'll take its natural log, and I need to multiply that by 3, so times 3, and I'm going to divide that by 4. Now I've calculated this number that should be up in the exponent, so I'll take e to that number, so do e to that number, I get 6.83, and now multiply by the initial amount, which is 13, so times 13, we have roughly here 89 micrograms of the bacteria.